Hello everyone, my name is Eriguchi. Today I talk about efficient noise generation to achieve differential privacy with applications to secure multi-party computation. This is a joint work with Atsunori Ichikawa, Noboru Kunihiro, and Koji Nuida. First, I introduce a multi-party computation. We assume players holding private inputs and they run some MPC protocol for a function f they want to compute. For example, some statistical analysis on private customer information. Then, after the protocol, an aggregator collects shares from all the players and reconstructs the value of the function f. Then, an adversary is allowed to corrupt a minority of players and seize their messages during the protocol. But if the protocol is secure, then the adversary learns nothing beyond the output. In this case, the output means the exact calculation result of the function f. So in standard MPC protocols, the adversary learns the exact calculation results. However, they possibly contain meaningful information on players' private inputs. For example, in MPC for private set intersection cardinality, players have private set, and they want to compute the cardinality of their intersection. But if the result is equal to 0, the adversary learns that there is no intersection, which will be meaningful information. So it is therefore important to appropriately process an output before we publish it. So therefore, in this work, we aim at MPC protocols outputting perturbed values by some appropriate noise. So to quantify privacy loss caused by releasing outputs, we focus on the notion of differential privacy. Roughly speaking, differential privacy requires that the output distributions are similar in some sense if the inputs are neighboring. Formally, a perturbed function by some noise drawn from a certain distribution D is said to be epsilon delta differential private if the output distributions satisfy this condition for all neighboring inputs. Here, inputs are called to neighboring if they differ at exactly one position. That is, their Hamming distance is exactly 1. Note that if epsilon and delta are very close to 0, then the output distributions seem to be similar. So differential privacy quantifies that intuition. So the simplest solution to achieving differential privacy is adding noise drawn from a certain distribution to the exact calculation result. There are many distributions that can be used for differential privacy. In this work, we focus on the two kinds of the noise distributions because they are very suitable to dealing with discrete data. The first one is simply as noise drawn from the discrete Laplace distribution. In this distribution, both tails exponentially go to 0. And the second one is based on the binomial distribution. It shifts binomial noise by its average and scales it by a certain scaling parameter. Then, if we choose these parameters P, M, and L appropriately, then these mechanisms satisfy differential privacy for any function f and any privacy budgets epsilon and delta. So in order to construct MPC protocols outputting perturbed values, we particularly construct MPC protocols computing a share of noise drawn from a certain distribution, such as discrete Laplace distribution or binomial distribution. Then, if such a protocol is obtained, players can can run standard MPC protocol for a function f they want to compute, as well as that protocol for noise generation. Then they can add a share of noise to a share of the exact calculation result, f of x. So an aggregator collects shares from all the players as usual after the protocol, but in this case, the output of the protocol is a perturbed value rather than the exact one. So the important point is that computing a share of noise can be done by jointly all the players using the MPC. Therefore, the adversary, corrupting a minority of players, cannot obtain the noise itself. So therefore, we can ensure that the adversary learns nothing beyond the perturbed result. So which means players' inputs are protected in terms of differential privacy. For the previous protocols for generating a share of noise, first, Duok et al. Proposed MPC protocols for the discrete Laplace distribution, truncated to a finite interval of integers, and for the binomial distribution. However, round or communication complexity of their protocol depends on privacy budgets, epsilon and delta. So to achieve high differential privacy, their protocols lose efficiency. And in addition, their protocol for the discrete Laplace distribution fails to generate a share of noise with non-negligible probability. So therefore, if it fails, it is necessary to rerun their protocol, which increases communication complexity. And there are other protocols for the continuous Laplace distribution and the Gaussian distribution with infinite support. However, these previous works do not provide concrete security analysis for differential privacy. Specifically, they assume infinite precision representation for real numbers and do not consider the effect of rounding or truncation. That is especially serious in the setting of differential privacy because differential privacy can be completely broken if their protocols are implemented with some bad finite precision representation. Now, in this work, we propose MPC protocols for generating a share of noise drawn from the discrete Laplace distribution over a finite field, a finite support, and for the binomial distribution. For the discrete Laplace distribution, our protocol is constant round, independent on privacy budgets for differential privacy, and always obtains an appropriate share of noise, which means the probability of failure is 0. And as a drawback, however, our protocol has higher communication complexity than the previous protocol. For the binomial distribution, our protocol is non-interactive in the online phase, while in the setup we have to pre-distribute several keys to pseudorandom functions. As a drawback, however, because we assume pseudorandom functions, our protocol only achieves a computational variant of differential privacy. And furthermore, our protocol loses utility. Specifically, the mean squared error between the exact value of the function and the output of the protocol is higher than the previous protocol. Finally, both of our protocols and security proofs only use finite precision representation. As a result, we can provide a concrete security analysis for differential privacy. Now, I show a comparison between the previous protocol and ours. Now, first I show it for the discrete Laplace distribution. Consider a situation where we want to achieve epsilon delta differential privacy for a function f with a sensitivity delta, which is defined as the maximum difference between the outputs on two neighboring inputs. Then we choose the parameter of the distribution p in this way, and we have additional parameters n and d to describe protocols under finite precision representations. Specifically, n corresponds to the range that noise is sampled from, and d means that all the real numbers such as p are expressed by using d bits. And to achieve epsilon delta differential privacy, we have to choose n and d sufficiently large. In this setting, a comparison is as follows. First, our protocol is constant round, independent of privacy budgets, while the previous protocol has round complexity depending on d. Furthermore, in our protocol, the probability of failure is 0. As a drawback, however, our protocol needs more communication than the previous protocol. However, that drawback is not so significant in practical parameter setting. For example, consider the case of these parameters, which are natural choice in the context of differential privacy. Then we can choose n and d as 30 and 50. In this setting, our protocol needs only 7 rounds, while the previous one 24 rounds. Furthermore, the communication complexity of our protocol is only 2.7 times higher, which will be acceptable. Note that the previous protocol failed with probability at 0.3 and then must be rerun, which increases communication complexity. Now I show a comparison for the binomial distribution. To achieve epsilon delta differential privacy for a function f with sensitivity delta, we choose parameters L and M for binomial noise so that this condition holds, where C1 and C2 are certain functions of delta. From the viewpoint of this condition, the parameter L should be chosen sufficiently large to achieve high differential privacy, while M should strike a balance between that privacy condition and utility in terms of MSE. In this setting, the previous protocol has communication complexity proportional to L, while our protocol is non-interactive in the online phase, at the cost of pre-distributing several keys to a pseudo-random function. As a drawback, however, due to our use of pseudo-random functions, our protocol is only computationally differentially private. And furthermore, our protocol results in higher MSE to achieve the same level of differential privacy as the previous protocol. Now, I provide a technical overview of our protocols for the discrete Laplace distribution. We first abstract the framework for distributed noise generation, which was implicitly used in the previous works. Specifically, we introduce a noise generator function. It's a deterministic function on m bits, such that if inputs are uniformly random, then the output is distributed according to a certain noise distribution. In this case, the discrete Laplace distribution with the finite support. And then we formally show that if a noise generator function is given, we can construct an MPC protocol for noise generation by combining a protocol for generating shares of uniform random bits and an MPC protocol for computing that deterministic function h. Theoretically, both these functionalities can be done by known protocols. But our technical contribution is that we provide a new instantiation of noise generator function suitable for the context of differential privacy, and that we construct a more efficient protocol for that deterministic function h than the generic construction. Now, construction of our noise generator function is decomposed into several steps. At an intermediate step, we first transform uniform random bits to some Bernoulli distribution. That transformation is based on evaluating an arithmetic circuit, while the previous one evaluates a Boolean circuit. Because arithmetic circuits are very suitable for MPC based on secret sharing, we can realize that that transformation in constant rounds. And then we next transform the Bernoulli samples to the discrete Laplace distribution directly, while in the middle of the previous construction, a sample from the geometric distribution is generated. Because the non-negligible probability of failure comes from that step, our protocol is able to avoid that failure. From now on, I explain these two steps in detail. First, to transform uniform random bits to the Bernoulli distribution, we use the following fact. For a uniformly random number between 0 and 1, define the bit b by this condition. Then the distribution of b is the Bernoulli distribution with parameter alpha. So roughly speaking, we discretize that procedure. Formally, we first generate d uniform random bits u1 to ud, and then we compare the binary fraction defined by the u1 to ud with the d-bit approximation of alpha. Then the distribution of b is now the Bernoulli distribution with statistical difference at most 2 to minus d. This is a formal description of our MPC protocol for transforming shares of uniform random bits to a share of the Bernoulli sample. Next, to transform Bernoulli samples to the discrete Laplace distribution, we prove that the following mathematical fact. For a sequence of Bernoulli samples with certain parameters, define L as a minimum index of bits being 1. Then the distribution of L multiplied by a random sign sigma is the discrete Laplace distribution with parameter p. If we truncate this sequence of Bernoulli samples, then the output distribution is the discrete Laplace distribution with finite support or specified by the length of the sequence. This is a formal description of our MPC protocol for converting shares of Bernoulli samples to a share of the discrete Laplace distribution. Now I provide the performance of our protocol. Our noise generator function needs nd plus 1 uniform random bits to generate one noise from the discrete Laplace distribution. For differential privacy, we have to take into account the effect of rounding and truncation. Specifically, to achieve epsilon delta differential privacy for any given non-zero delta, we have to choose sufficiently large n and d so that this inequality holds. Note that both terms in the left-hand side converge to 0 as n and d go to infinity. For complexity, our protocol needs approximately nd multiplications to compute our noise generator function, and also need to generate nd plus 1 uniformly random bits, which can be done by at most nd multiplications. So because these functionalities can be done in constant rounds, so the round complexity of a protocol is also a constant. while our protocol needs totally and the multiplications in the order. Next, I provide a technical overview for the binomial distribution. Recall that the binomial mechanism shifts binomial noise by its average, and then scales it by a certain scaling parameter. So then, if we choose parameters m and l carefully, that mechanism satisfies differential privacy. So before explaining our protocol, I first introduce pseudorandom secret sharing. Our protocol is essentially based on this primitive. Pseudorandom secret sharing enables players to non-interactively compute a share of a pseudorandom number over a prime field, assuming a pseudorandom function. In the setup, we have to predistribute n choose t keys for the pseudorandom function. Specifically, each player receives some part of keys. Then each player computes pseudorandom numbers using their keys over some public input A. And then they compute a certain linear combination of these values. By carefully choosing these coefficients, we can see that it is indeed a share of their sum, which is also pseudorandom. Note that the online phase of that protocol is non-interactive. So now our protocol is based on the following simple observation. If we encode elements in the prime field into L bits, the number ones in a pseudorandom number looks like binomial noise with parameter L from a viewpoint of PPT adversary. So specifically, as in pseudorandom secret sharing, each player evaluates the pseudorandom function using their keys. But in our protocol, they count the number ones in these values, which seem to be following the binomial distribution with parameter L. And then they can locally compute a share of their sum. As a result, players non-interactively obtain a share of binomial noise with the parameter LD. However, our protocol loses utility to some extent. Consider an adversary corrupting T players. He obtained their keys, and due to the construction of pseudorandom function, pseudorandom secret sharing, there remains only one key unknown to the adversary. This means that there remains only one noise following the binomial distribution. Consequently, we can only ensure our protocol achieves the level of differential privacy provided by the binomial distribution with the parameter L. On the other hand, our protocol adds binomial noise with parameter LD. So therefore, our protocol results in n choose t times higher MSE. Finally, I summarize this presentation. In this work, we propose efficient MPC protocols for generating our share of noise drawn from the discrete Laplace distribution and the binomial distribution. Our protocols can be used to construct differentially private MPC protocols by perturbing the exact calculation results. Our protocols provide trade-offs between round complexity, communication complexity, and utility. Future work will be further efficiency improvement. And in addition, because in this work we only deal with integer data, it would be important to extend our protocols to floating point representation. These are the references. This is the end of my talk. That's all. Thank you.